We're going to remind you of two facts that we're going to be using throughout. The distance, folks, the distance between a point, the distance between a point and a line is measured at a right angle. The distance between a point and a line is always measured at a right angle. So if you have some line here and you have a point, the distance is always measured down here at a right angle. It is never measured at anything else. It's never measured at anything other than a right angle. Always this distance. In addition, an angle bisector, just to recall, is a segment or a ray that divides an angle into two equal angles. Okay. These two old definitions. Our angle bisector theorem, kind of the new statement about angle bisectors is the following. It says that any point on an angle bisector if you're a point that's on an angle bisector, then you are equidistant from the sides of the angle. Is the angle bisector. The converse is also true. If a point is equidistant from the sides of an angle, then it must be on the angle bisector. Picture is pretty similar. So if you have an angle here, and you know that it's the same distance away from the two sides, then you can conclude that it must be on the angle bisector. Then you have to be able to draw the angle bisector through it. So we can use each of those two things as one example of each. If you want to find, if you say using the first idea, if the point is on an angle bisector, notice that ray BD is bisecting angle ABC. It's the two is divided into two equal parts. Then any point on this ray is equidistant from the two sides. Namely, if you drew at point D, if you found the perpendicular distance to A, that's the same as the perpendicular distance over here at point C. So what is the measure of segment AD? It's got to be the same as DC. It would be application of the first of the perpendicular bisector, or excuse me, the angle bisectors there. Similarly, if you know that, say, this point is the same distance from each of these two sides, measured at a right angle, then what do we know about the ray that's going through it? What is this ray called? Got to be an angle bisector, because this point is the same distance from the two sides. Therefore, this is an angle bisector, so then what do we know about the two angles that's being made? That they're the same. So therefore, 6x is equal to 2x plus 16. Therefore, x must be 4. The point where the three angle bisectors of a triangle meet is called the incenter, or the point of concurrency of the angle bisectors of a triangle. This point is called the incenter. Yesterday we had the circumcenter, which is where the perpendicular bisectors met. When we cut the sides in half at a 90-degree angle, they met at the circumcenter. If we cut the angles in half, those three rays intersect at the incenter. These 2 points are not necessarily the same. If you're in an equilateral triangle, you can prove that they actually are the same. But if you're not an equilateral triangle, it's not really that difficult to show that they're usually not at the same spot. They can be close to each other, but they're generally not the same spot. The incenter is always on the inside of a triangle. It's also called an incenter because this is the point. This is the center where you can draw a circle around this point, and the circle is entirely inside the triangle and will just touch the three edges of the side. Will be what's called tangent to the three sides of a triangle. The circumcenter actually does the opposite of that. That's the point where you can draw a circle around that point, and it just touches the three vertices of the triangle. You can circumscribe the triangle. You could actually, the triangle will be totally on the outside of the circle. So let's take this as kind of the next step. If this incenter is on the three angle bisectors, then what do we know about the distance, say, from this point that's on the angle bisector to each of the sides of the triangle? It's equidistant. This point, since it's on this angle bisector, is the same distance from this side as to this one. It's on this angle bisector, so it's on the same distance from this side as to this one. And it's on this angle bisector, so it's the same distance from this side as it is to that one. Or more to the point, the incenter theorem says that the incenter of a triangle is equidistant from all three sides. Distances measured at right angles. So if we draw the segment from the point to the triangle at a right angle, then that has to be the same for all three sides. Like in that first example. I'm going to creep it down a little bit. If I say T is the incenter, T is the incenter. According to the incenter theorem, it's the same distance from all three sides. So if we draw a segment from this point to each of the three sides at a right angle, those things have to have the same length. So then what's the length of ST?
15.
That means this segment is the same length as this segment, which is the same length as this segment. Well, they're all 15. In center is measured to sides. It's the same length to the sides. Cut the angles in half, it's the same length to the sides. Oh boy, how about the next one? P is the incenter of this triangle. So what segments are all forced to be the same length in this triangle, first of all? Okay. Okay, QP has got to be the same length as what segment? These three things all have to be the same length. Why? Because P is the incenter of this triangle. How can we use that to find what x is? Well, where are some measures that we actually have here?
Well, because you have the 12,
Yep.
you have 12 and 13, and you know that US has to be 12 too. I'm wrong.
Where?
US. No, I'm wrong. Never mind.
No, we don't know anything
No.
about those.
Yeah.
Would you use some reverse diagram here to find
I mean, it wouldn't be reverse, it would actually be just the Pythagorean theorem.
okay.
Since these are all the same length, that means this thing is x. Which means you have a right triangle of x, 12, and 13. And if you ever want to find the lengths of a side of a right triangle, you can always use the Pythagorean theorem. And remember what the Pythagorean theorem says. Our favorite Greek theorem, a squared plus b squared equals c squared. How do you know what a and b are in a right triangle? How do you know what c is? How do you know what angles like are? C is the hypotenuse. C is always across from the right angle. Find the right angle. Whatever angle is opposite of the right angle is C. Does it matter what the other two letters are called? No. So if you want to say this is A and that's B, that'll give you the same answer if you say this is A and that's B. Either way, the equation you could set up would be 13 squared equals x squared plus 12 squared. If you flip-flop those, then you get the same answer. If you flip up x and 12, you still get the same answer. So to solve this, what do? I just take the square root of both sides, and then I have x is 1? No. What should we actually do? Square both sides. Actually figure out what the squares are. Subtract 144. X algebraically is plus or minus 5. Plus or minus 5. Do we keep both answers or do we throw one out? Why do we throw one of them out? Because our problem is a geometry problem. We can't have a negative side length. So we'll stick with just the positive value. So therefore, this is 5, and therefore that's also 5. If you want, so we've had 3 segments so far that'll show up in your quiz. You had a mid segment. How do we find a mid segment? That was from Monday. Mid segment. What points do you think we're connecting in a mid segment? Connect midpoints And I would definitely check out the mid-segment theorem that we wrote down. It said that the mid-segments are half as long as the opposite sides. You may want to recall that for tomorrow. Then we had the perpendicular bisectors, and said that the incenter said that any point on a perpendicular bisector is equidistant from endpoints. And then today we had angle bisectors, which are any point on an angle bisector is equidistant to the sides. Okay, be the three things.